Okay, this is part 2 of the properties of sound video. So the first one I wanted to do is this one with the speaker. So if you read it carefully, the speaker is moving towards point A, which means your wavelengths will be shorter. And if the wavelengths are, because now as the waves are being made, the speaker is moving with those waves. So you should hear a higher frequency and a shorter wavelength. So the answer to that should be B. So that's pretty much conceptual. You don't have to do any math for that. Let's look at 63. Now, the observer is stationary. The train is moving towards the observer. So we're going to use this formula here. And we have to make a decision when to use a plus and we need to use a minus. Now, in here, the observer is not moving. Now, if the train is moving towards the observer, we should hear a higher pitch. We should hear something higher than 500. The only way you would get that is by putting a minus down there. Okay, you can go back to the formula. It kind of like talks about that. Now, if the train is moving away from the observer, well, let's see what happens. Now, the observer is expected to hear something less than 500. The only way mathematically you can get that is that if you make this fraction here less than 1. And the only way you can do that is by adding VS at the bottom, by putting a plus at the bottom. Okay, and then you can put stuff in the calculator and see what you come up with. All right, 64. An ambulance travels down a highway at 75 miles per hour. It's got that frequency. A car is traveling at this speed towards the ambulance, right? So let's just say this is the ambulance, right? Here is the car. Okay, so this one is going at 75 miles per hour. This one is going at 55 miles per hour. Okay, so and this one is generating 400 hertz frequency. So again, it's going to be 400 V, the observer, V, the source. Now we're going to say that it's speed of sound in the air on this day. I said that the temperature is at about 20 degrees. So the speed is about 343 degrees, roughly. So I have two things that are in miles per hour. So I'm going to leave everything in miles per hour, which means the V, the speed of sound in air, is 343 meters per second. I'm just going to change that one. I'd rather change one thing than two. So that's 772.88 miles per hour. And since this is just a ratio, as long as all the speeds have the same unit, it doesn't matter. Okay. Now, let's see. The car is coming towards the ambulance. Okay? So a high frequency is expected. So a plus goes in there. Okay? The ambulance is going towards the car, right? So again, a high frequency is expected. So in order to expect a high frequency from the ambulance moving towards the car, should be putting a minus here. Okay? And then you can put in the numbers and you got it. So the trick is just to figure out which one is plus and which one is minus. Okay. Okay, so now let's look at the other case. So now the ambulance passes you at 75 miles per hour. Let's see what changes here. Okay. So now if the ambulance passes you, the car is going away from the ambulance, so it should hear a lower pitch. Okay, so this should be a minus. But the ambulance is also going away from the car. Okay, so we should expect a lower pitch. So in order to expect a lower pitch, you have to make this bottom greater. So you have to put a plus in there. And then the rest is just plugging numbers into the calculator, just to know what to put in. So the observer here is the car, and the source is the ambulance. Okay. Okay. All right, let's look at the 65. A car traveling at 100 kilometers per hour sounds its horn as approaches. Blah blah blah. Okay, so I think I changed the 100 kilometers per hour to meters per second. So I made that 27.78. So this is 27.78 meters per second. 0 degrees means about 331.5 meters per second for the speed of sound. So this is V. The car is the one that's sounding the horn, so this is V source. Okay. What is the frequency of sound wave hitting the hiker? So we're going to just assume that the hiker is not moving, or maybe moving at a speed that is way, way, way less than the speed of the source. So it shouldn't make that much of a difference, even if they just walk in a low speed. So as the car approaches, okay, so here is the car, here's the hiker, right? So we're going to assume that he's not moving. So the car is going in that direction. So let's say, so it's going to be 440 V, VO, V, VS. So we're going to assume that this observer is not moving. Now we have to make a decision whether to put a plus or a minus there. So as the car approaches, this hiker here should hear a higher frequency. So in order to hear a high frequency, we have to put a minus down there. Okay, and the rest you just put in the numbers. Let's look at the case where the car passes. Okay, so it's going to be 440 V, VS, and now we should expect a lower frequency. This person here is going to hear a lower frequency. So the only way that can work is by putting a plus in there, and then you can just plug in the numbers. So I'm just spending the time figuring out when to put a plus and when to put a minus. And I don't want you memorizing this, you just have to think about it. Okay, just think about what should happen in each case. Right. If you're standing at a railroad crossing, so you're standing, so your V observer is 0. The train is approaching at 100 kilometers per hour. So I think we just did that before. It's 27.78. So that's the source. That's what's generating the sound. I think that's what it is. Yeah, 27.78. Okay. The temperature is 20 degrees, so the V is about 343 meters per second. That's the speed of sound in the air, so 343 and a half. Okay. What is the frequency you hear when the train approaches? So the train is going this way. You're standing there, so it's going to be 400 V, the observer, V source. So you're not moving. Okay, so let's make a decision about whether to put a plus or a minus at the bottom. So if the train is coming towards you, you're going to hear a higher pitch. Okay? So the only way that can happen is by putting a minus here. And I hope you can see that if I put a plus here, right, I'm going to end up with something less than 400 at the end. So you just have to know your fractions. Now let's look at the case where the train passes you. So when the train passes you, you expect it to hear a lower pitch. So if you want to hear a lower pitch, you have to make sure that this fraction was less than 1, so to end up with something less than 400, so you got to put a plus there. It's as simple as that. Okay. Okay. So 20-degree day, so the temperature, the speed of sound is 343 and a half. The frequency heard by a moving person from a 500 stationary siren, so the VS is 0. Okay, so basically what's being made is 500. What's heard is 520. Okay, is the person moving towards or away from the siren? Well, I guess they have to be moving towards it because otherwise they will not hear a higher pitch. So what's the person's speed? Okay, well, so we're going to do, after writing the formula, of course, we're going to say, well, this is what they hear. This is what's made. Okay, so the source is not moving. Now, in order to hear 520 when 500 is being generated, I think you can see that we should put a plus here. And we can just do the algebra. So how do you do the algebra is up to you. So I'm going to put in a 343 and a half here, put in a 343 and a half here, and I'm sure you can figure out the algebra here on your own. So I'm just showing you how to set it up. All right, let's look at number 68. A bicycle rider is approaching a factory whose whistle is blowing, right? So the factory is now moving. So Vs is 0. Temperature is 23 degrees, which translates to 345.3. V is 345.3. That's the speed of sound in air at this temperature. The frequency is 555 hertz. That's the source. If the rider hears a frequency of 579, so they're going to hear something higher. So how fast is he approaching the factory? Obviously, they have to be approaching because they're hearing a higher frequency. So let's see what we can do here. So they're hearing 579.3. What's being generated is 555. And we have to fill in the pluses and minuses. But the source is not moving, so that's a 0. All right, so this here, actually, let me figure out the plus and minus and then we'll do the rest. Okay. Now, we're hearing something higher than 555, so you can probably see that this should be a plus, otherwise it won't work. Okay? Now, you plug in 345.3, right? Plug in 345.3. This is just like the other one. And you can, sure you can handle the algebra. Okay, and the answer should be 15.12 meters per second. All right, let's look at 69 here. Okay, a car approaches you at a constant speed, sounding its horn, and you hear a frequency of 76 hertz. After the car goes by, you hear a frequency of 65 hertz. Okay, so let's see how we can do this. Okay, so you pretty much stand in. All right. So I'm going to set up two equations. One equation for when they're coming at you, and one equation for when they pass you. So when they're coming at you, so here's the car. This is you. Okay. So your equation should be. You hear 76. You're going to hear something bigger than what's being generated. So here is the frequency of the source, V, the observer, the source. Well, this observer is not moving. Okay, this is 343. And I should have done the plus and minus first, but that doesn't matter. Okay. Now, if we hear something bigger than what's being generated, I think we should put a minus here. Because you want to make the denominator smaller than 343, so you end up with something bigger than what's being generated because you're expecting a higher frequency. Okay. Now the other equation would be, well, the car passes you. Okay, so it's going to be you're going to hear something lower than what's actually being made. F into 343 over 343. Now, if you're going to hear something lower, you have to put a plus here, plus V source. Okay? So now to figure out the frequency that's being generated, what you can do is you can probably, there's a bunch of ways you can do this. You can find Vs. Okay, set up a system of equations. Okay, I'll show you how to do it. So let's try this. All right, so I'm going to do this. I'm going to do 76 times 343 minus Vs over 343 equals, so this is F. Okay, you should be able to do that here. And then I'm going to do the same thing for F on this side. So that's going to be 65, 343 plus Vs over 343. Okay? So these two are equal. So you can see that the 343 will go away, and you can solve. Okay? Another way you could do this is isolate Vs in this equation, isolate Vs in this equation, and set these equations equal to each other. So that's one way. So here you're going to find Vs and come back and plug it into either one of these equations to get the frequency. The other way is to do this. So do 76 times 343 minus 76 times Vs equals 343 F. And then I'm going to isolate Vs here. So Vs is going to be 76 times 343 minus 343 F over 76. Okay, and I'll do the same thing on this side. So I'm going to say 65 times 343 plus 65 Vs equals 343 F. Okay? And I can say that Vs equals 65 times 343 minus 343 F over 65. Okay? So once you have it like this, you can set this equation equal to this equation, and you can get F directly without having to find the velocity first. Okay. Okay, so let me just try 70. Okay. You're driving along a highway at 35 meters per second. When you hear the sound of a police car approaching you from behind. So this is your car. This is the police. Okay? So you're going at 35 meters per second, and we don't know how fast the car is going, so probably don't care. Okay. What is the frequency of the silent police? The speed. Okay. So we have the speed. All right, let's try that. So let's do two equations. One for when the police car is coming at you, and one equation when they leave you. Okay, so when they're coming at you, you should be here in 1310 equals frequency that's being made, V observer, V source. Now the V source is the speed of the police car. All right, so now we have to put in, well, I'll leave this for now like that on this side. Okay, now let's look. The car is going away from the police car. So the car is going away from the car. So we should expect a lower frequency. So this should be a minus. The police car is approaching the car. Okay, so we should expect a higher frequency. Now to expect something higher, you have to lower the denominator. So you put a minus down there. Okay, so that's one equation. Now we can put in some numbers here. So we're going to do 343, and this is 35. Okay, I think that's what I have. Yep. Now let's look at the other side. Now, the police car passes you in this part. So I'm going to do it here. Police car passes you. Okay. Now, in here, you're going to hear a lower pitch because they're running away from you. Equals F, V, the observer, V, the source. So let's think about that for a second. Now, you're going towards the police car, so you should expect a higher frequency. So I've got a plus in there. The police car is going away from your car, so that should mean a lower frequency. Now, to get a lower frequency, you have to make the denominator bigger. So you put a plus down here. Okay. Now you plug in the numbers. So this is 35, 343, 343 down here. Okay. And if you look at these equations, it looks very similar to the one from number 69 we did earlier. So now two options here again. You can solve for Vs in both of these equations, then set the outcomes equal to each other, and then you can go directly for the frequency. Or or you can actually find or isolate the frequency in each one of these equations, set these equations equal, find Vs, and then come back to either one of these equations and find the frequency. So the answer should be C. All right. Let's look at number 71. You are moving at 120 kilometers per hour towards a stationary train. So that's 120 kilometers per hour comes out to be 33.133 meters per second. The source has no speed. The train blows, it's 0.4 kilohertz, so you got to be careful with that. So it's 400 hertz. Take the speed of sound to be 340. What frequency do you hear? Well, let's see what we hear. Okay, so this is what we're going to hear. F equals, so F prime, F O, whatever. It's going to be 400. Okay, so this is gone. The source is now moving. Now, you're moving towards the train, so you should hear a higher frequency than 400. So right away, you can probably have eliminated C and D. Okay? All right. Now here we're going to put in 340. Here we're going to put in 33.33, and the rest is just plug it into the calculator and come up with the answer. All right, let's look at this RT17. All right, in case A, it looks like the relative speed is positive 10. In case B, it looks like the relative speed is 20. Okay. In case C, it looks like the relative speed is 10, but they're going further away. So I think we can say that it's negative 10. So basically, the police car is with respect to the motorcycle, is going to feel like it's going backwards. And here, the relative speed is 0. So the ranking should be B, A, D, and then C. Because here you're going to hear the same frequency. Here you're going to hear a lower frequency that you hear when they are going at the same speed. So technically, they are pretty much stationary with respect to each other. I'm not going to read this, but Brooke is the one that's correct. Okay. Even if you are not accelerating, just the fact that the source and the observer are approaching each other, that's going to give you a higher pitch. Okay. Now, if the source is accelerating or the observer is accelerating one towards the other, what you're going to hear
a high but change in pitch. Okay, so it's not going to be the same pitch, in other words. But if it's going at a constant speed, you're just going to hear a high pitch, but a constant high pitch. Okay, so don't let the acceleration fool you there. You're going to hear a high pitch no matter what. The difference is if it's going at a constant speed, you're going to hear a constant high pitch. But if there is acceleration, you're going to hear a high pitch, but a change in high pitch. Okay, RT19. So we have a beat frequency of 5. So which means, okay. So the tuning fork has 512, so which means the guitar string can be either 507 or 517. The tension in the guitar string is then increased, after which the guitar and tuning fork together create a sound wave, the beat frequency of 4 Hertz. So which means it's 508 or 518. When you increase the tension, you're basically increasing the frequency. And here's why. V equals square root of tension over the linear coefficient, linear density. So if the tension goes up, the V goes up, the lambda stays the same because the length of the string stays the same. So if V goes up, the frequency has to go up. Okay? So the only one that can work is 508. Okay? So it should be less than 512. Part B, I think I already answered when I was doing part A. Okay. I'm going to drop a siren in water, right? All right, so the frequency stays the same because the frequency is basically what's generated by the siren. But when you go in, so I'm going to write V equals lambda times frequency. When the siren goes inside the water, the velocity increases, the F stays the same because that's what's being generated by the siren, so which means the wavelength will have to increase. As you are moving very quickly towards a speaker emitting a pure tone, which characteristics of the sound get larger? Well, it's going to be louder, okay? And the frequency has to get higher. It's a higher pitch because the source and the receiver and the observer are approaching each other. Okay, now we're into resonance. Okay, a musician stands outside in a field and plucks a string. Okay, so you're going to have standing waves, meaning like you're going to have that resonance, just like we did in the labs. So the string is going to definitely have standing waves, and it's also the air inside the guitar, right? Because the air inside also vibrates and will create a standing wave. Now we're into beats. Okay, so you have a tuning fork at 440 Hertz played with another tuning fork, so 437. How many beats will be heard over a period of 10 seconds? Well, the beat frequency is 3 Hertz, okay, which means 3 cycles per second. So in 10 seconds, you're going to have 30. Okay, 2 tuning forks are producing 15 beats every 5 seconds, so that's 3 beats per second. Okay, one of the tuning forks has a frequency of 250 hertz. What 2 frequencies could the other one have? Well, it's basically going to be 3 off from 250, so it's either 247 or 253. Okay, 74. 2 strings both vibrate at exactly 819 hertz. The tension in one of them is then increased slightly. So if you increase the tension, you're going to increase the frequency. Okay, as a result, 6 beats per second are heard when both strings vibrate. What is the new frequency of the string that was tightened? So the beat frequency is 6. So the frequency of the other one is going to be 6 off from 819. But because you increase the tension, you also increase the frequency. So only the one that's 6 above is going to be correct. So it should be 825. If we had decreased the tension, it would be 819 minus 6. Let's look at 75. Well, this is conceptual. This is pretty much the concept of resonance, right? So the answer should be A. Okay, 2 tuning forks producing beats. So we have 2 tuning forks that are played at the same time, and we get a beats frequency of 9 hertz. If one of the tuning forks has a frequency of 480, then the other should have a frequency of 489. False. The other one could be 489, or it could be 9 less than 480, which is 471. Okay. RT22. 2 different wave sources, beat frequency at various location. Okay. Okay. It's going to be all the same because the pitch is independent of the distance. Okay, and that's it, because RT23 is a repeat of RT16. I didn't notice that. All right. Thank you.